All right, so good morning, everybody. Today is my fifth run of the conference hours, and I'm going to be giving a plenary talk on how to use the equation, in specific, the conservation of momentum that we see displayed here. And so with my last video, we dissected this equation and we labeled that this was the initial mass of some object we decided to label 1. It's very arbitrary. V1I is the velocity associated with that object that we chose to be 1, and it's the initial velocity. And then you can say the same words that I just said about that, but apply the object to a second object, and we label that object 2. So if we consider some problem where these two objects, 1 and 2, are colliding with each other, then we can use conservation of momentum to find out quite a bit of information of the system afterwards. In fact, this is intuitively what police officers use when they're, dissecting, who's at fault or who's responsible during a collision, car accident. Car accidents happen to be inelastic collisions. This is where the two objects stick together. And we know that this leads to very certain circumstances for the conservation of momentum equation. Now, they're not doing math or anything, but they're using the physical concepts to say, okay, yeah, this makes sense that this person must have been coming from this direction for this collision to have occurred. So with that being said, we will continue. And so being that I've been doing physics for a while, I've probably done this question at some point in time in my life, but I tried to find questions that I just don't remember. And I did it intentionally because I want to run through this, my thought process with you guys. And so this is what I think that the true mission of these videos should be, not necessarily answering the question, but how to answer the question. So the first problem that we're going to solve is similar to what I just opened the video with, and that is, a 6-kilogram ball is thrown west at 20 meters per second and collides with a 14-kilogram ball while in the air. If the balls stick together in the crash and fall straight down to the ground, what was the velocity of the second ball? Okay, so to make sure that we're not reading this blindly and that we're not just reading a bunch of words and just saying them, we should ask ourselves some questions about what we just read. And so the questions that we should ask ourselves, fall along the lines of these bullet points here. And so what information is given in the problem? What concepts, equations could we use? Are there multiple ways to solve the problem? How do we know we've chosen the right one? Do we understand what the question is asking? Try explaining the question to something or someone. Anything that's willing to listen. The point is for you to say the words your mind is thinking and see where you start lacking confidence. So let's run through this real quick. I'm hitting all these extra buttons. So what information is given in the problem? Well, we see that we have the mass of some ball is 6 kilograms. Let's call this ball 1. And we're going to say that this is its initial mass. And it says that it's 6 kilograms. Okay. All right, and we're told that it's moving west at 20 meters per second. So V1I is 20 meters per second west. This is important. We'll draw pictures and things, or I will attempt to draw pictures to make this make sense. But first we need to, pull all the information from the problem. So then from there, we're told that it collides with a 14-kilogram ball while in the air. Okay, so this 14-kilogram ball, we're going to label that object 2. And we're going to say that its initial mass, 14 kilograms. Okay. Now, we're not told anything about its velocity, but we are told that the balls stick together during the crash and that once they collide, they fall straight down to the ground. Okay. So the information here that is given is that the balls stick together in the crash and fall straight down. This piece of information is important. What does it mean? You notice that I'm running through thought process here. So what does this information mean? This information means that once they collide, there's no momentum. Once these two objects collide, there is no momentum. So their final momentum is zero. Why? Because we want to always rationalize with ourselves. We're always at battle and at odds with ourselves. So we always have to ask ourselves why when we're doing these problems. So why is the final momentum zero? Well, because when the two balls collide, we're told that they fall straight down to the ground. We're told that there's no velocity or up motion going in the horizontal direction. So the fact that there is no motion in the horizontal direction, or if you want to call it X, this means that their net moment or that their momentum is zero. So we have just rationalized with ourselves what information is given in the problem. So the first thing, or the next thing that we need to do is ask ourselves, what concepts or equations could we use? Well, being that this video has a theme and you were told what was going on at the beginning of it, there's obviously a hint here, but most of the time you're not going to have that hint other than that, hey, we studied these concepts in this module, which it kind of narrows down the list of things that you could use. So given that we're at an unfair advantage for this question, the concepts and equations that we could use would be conservation of momentum. The reason why is because we have a mass, we have a velocity, we have another mass, and we're asked for a second velocity. And then we're also, the true keyword in all of this is this word, collides. If you see the word collides, most of the time it's going to be a momentum problem of some sort. So going through, we're answering these questions. We said conservation of momentum. Why? I just answered that. We are given a mass, masses, and velocities, or we were given a mass and a velocity, and then asked to find a mass, or asked to find a velocity. Then we saw the word collides. These are good indicators that we should use this concept. So are there multiple ways to solve the problem? Yeah. How do we know we've chosen the right one? Well, we don't know for a fact, but we have plenty of information to make sure, or to point us in this direction. Okay, do we understand what the question is asking? This one here is not so much for me to go over with you because this is sort of an inward. In fact, if you read this here, it says, try explaining the question to someone or something, anything that's willing to listen. This is called the rubber ducky method by computer scientists, and it's also called the Feynman method by other people. Literally means just take something that maybe you want to give it a personality and it's dumb, and you're trying to teach it what you're trying to do. and you're trying to explain it to it, this object, what you're doing. And so the point is not for the object to do the problem for you, but it's for you to start thinking about what it is that you're doing, for you to say these words out loud, and for you to see where you lack confidence in your explanation. Because once you reach that point of lacking confidence in your explanation, you need to stop explaining, and then you need to go back and find the information that you were just stuck on and reread it again. And then you will eventually pick up on what it is that you're supposed to do. And I guarantee that you will learn this stuff a lot better. This method has been proven to work countless times through several studies. So now we're at the point where we've gotten all the conceptual knowledge that we need. We're now ready to attempt to solve the problem. Okay, so we said that we were going to use the conservation of momentum. And I'm going to go ahead and just get that from up there because that's a big gnarly equation. That's the next problem. Okay, and let's recollect our information and just bring it down. Well, for me, I'm just going to bring it down. You guys probably have it on a page. All right. Now remember, we said in this problem, in the conceptual part, that our final momentum was 0. Remember that our final momentum is 0. Therefore, we can rewrite the equation. Like this. And so now we literally have everything that we need except this, which is what we're looking for. We're looking for the initial velocity of the second object, which was the 14-kilogram ball. So for me personally, they always trained us to solve these equations first. Don't start plugging numbers in. That's just more you have to write. And then that's more you have to keep up with. So it's better to just solve for your answer now instead of continuing and then more writing. And then that's more likely you're going to miss something or mistype something in somewhere. So I'm going to move object 2's, I'm going to move object 1's parameters over to the right-hand side of the equation. So that way it yields real quick side note. As I get older, for some reason, I associate letters with numbers, and my S's are 2's, my R's become 4's, and it's a rather strange phenomenon. Anyway. All right, and so now we want to solve the equation for our second object's initial velocity, so we need to divide both sides by m2I. Okay, so now we can, we have all of these numbers. We can plug these things in, and we can say that E2I is equal to negative, let me just do this like this. So M1 is 6 kilograms. Let's just go ahead and make sure we add the units in too. We have 20 meters per second. One thing that I forgot to point out here is that, and it's specifically here, the reason why I'm bringing this up is because it matters right now. I forgot a negative sign right here. And I want you to think for a second why I forgot, why I need this negative sign here. The reason for this is that if we think about east and west being positive and negative x direction, or negative x-axis, positive, negative x-axis, the west direction is the negative x direction, and the east direction is the positive x direction. So therefore, this picks up a negative sign because it's in the west direction. So that means that here, we add in that negative sign. So now we have in the denominator, we have our second object's initial mass, which is 14 kilograms. So now we see here that we have a velocity on our left-hand side, and the units of velocity are meters per second, or length per time. And so that means that our kilograms need to cancel, and they do. So this is great. We also see that our negative signs cancel. And what we have here is 120 divided by 14 meters per second. Okay, and because it has a positive sign, we can say that this is east. This matters because if you look back at the problem, well, let me just save all that. Instead of explaining this, we're going through the thought process. So get out a calculator real quick. Okay, I calculated 8.7 or 8.57. Okay. And so now we have our initial velocity. Does this velocity make sense? Well, oh, I'm sorry. Let's go through this first because we're getting there. Do we get stuck? We didn't get stuck. But if we do get stuck, we need to reconsider the problem, perhaps reread the question and repeat the steps. So this is an opportunity here, if you get stuck, that you go back to this point and try explaining the question to someone or something or anything that is willing to listen. So from there, you continue. So now that you have an answer, you ask yourself the remaining question, does our answer make sense? Is it reasonable given anything that we can relate it to in the real world? So does the, as we're doing this, these sub-questions, does the answer yield the proper units? Well, yeah, we said that this yields a meters per second because it's a velocity. Do the numerical answers coincide with what we would expect from the situation? Well, that's the question that I stopped at before I started reviewing these. Does this number make sense? Well, yeah, it makes sense. The reason why is because if we look at this equation, if we look at this equation here, let's go ahead and plug these numbers in just to kind of see what's going on here. So M1 is 6 kilograms. Let's make sure that we leave these units in here. Velocity is negative 20. 14. And then U2I. Okay, so this object 1, is lighter than object 2, but it's moving faster than object 2, as we found. This makes sense because this, being smaller, would have to move faster to have a momentum that is equal to the momentum of a 14 kilogram object moving with some velocity. So the velocity of the larger object needs to be smaller than the velocity of the smaller object, which we found in magnitude. So answer to this question, yes, this does yield the proper units. Does the numerical answer coincide with what we would expect from the situation? Yes. Oops. Yes. The heavier ball, our object, has a smaller velocity. Okay, so just to make sure you guys get this, and I really want to make sure because we're getting into the harder stuff, and I want you guys to be well prepared. So I have another problem that I'm going to run through this, and I want y'all to fill in the blanks. So what we have here is a 10-kilogram ball moving at 13 meters per second strikes a ball at rest. After the collision, the 10-kilogram ball is moving with a velocity of 7 meters per second. What is the velocity of the second ball? So what is the information that we're given? We're given an M1I if we call the 10-kilogram object ball object 1. We're given a V1I, a velocity of that object at 13 meters per second. We're given the initial mass of a second object. I'm sorry. We're not given the mass of the second object. We are told that the final velocity, or the final mass of the 10-kilogram, or I'm sorry, that the final velocity of the 10-kilogram ball. Sorry, I'm fixing these. Is 7 meters per second. And we're not given any other information numerically. So how can we solve this problem? So we know that V2I is at rest, has 0.0 meters per second velocity. It doesn't say anything about the mass of the second ball. So we're kind of left with just this. Okay, so now we already know that we need to use conservation of momentum. And given the situation, we can rewrite conservation of momentum in this way. And so now everything we have here, we pretty much have everything except the second mass, which is probably gonna become a problem. And I think that it is because we need to use also conservation of kinetic energy, or conservation of energy. Well, this is 0 for I. Okay, and so with these two equations, we have two unknowns and now two equations. And so algebraically, we need to solve one of these for either M2 or V2, the final velocities, and plug it into the next. For time purposes, I only wanted to make this a 15-minute video. I want you to do the algebra and see if you can come up with the proper answer that there is for this question. I will tell you that the answer for this question is something small. Got rid of the page on accident. I found it again. Oops. The answer to this question is 3 meters per second. All right, so that will conclude Plenary Talk 5. If you have any questions, please email me. I will post the link to this here soon. Have a good day.